Hello, my name's Ezekiel Cater, and I hope you're enjoying MongoDB.live. I'm personally really excited for a lot of the great content coming up, but for now, I want to talk to you about building reports 10 times faster. And we're going to be utilizing pipelines and streams to get that done. So I'm going to cover what are pipelines, what are streams, what is back pressure, and how do we use all three of those together. And then I'm going to do a quick live demonstration. So to get things started, let's pretend we're at this new company, and this new company needs a report for all their great users. So we get the requirements from product. The report needs to have a custom date range, so that way the user can ask for the start date. The report also needs to integrate with some external data. So we have some third party that provides additional analytics on our data, perhaps, and we need to integrate that, make some modifications, and then when we're all done, we need to save that data as a CSV to bucket storage. That way we can give the user a link to download this data. So we get started, and here's kind of like our first initial implementation we do. We build an aggregation. We query for any documents that have a start date greater than the start date that was given. We pull all of that data into a variable called users. We then call some function that gets the external data and integrates it, makes those modifications, and returns the final data. We then stringify our final data, and then we save that final data as a CSV. In this example, we're saving to our local file system, but in our production, it's going to write out to bucket storage. So we deploy this report. Most of our customers are ecstatic. We do have a few complaints that the report's a little slow for our big customers, but everything's working. So some time goes by, and customer service contacts us and says, hey, we got this customer that is not getting their report, and they've tried several times. All right, interesting. So we pull up that customer's reports, and we see something we never expected we'd ever see. This customer is requesting 1 million user records out of our system. Well, that's interesting. I don't know if we can even accommodate for that, but we all get together and we start thinking about what are the issues we have and how can we address them. So first, we want to identify what's the slowest part of our report. And once we do, is it even possible for us to scale up that piece? And how long does it take for us to begin processing our first records? Are we working on them right away? As we saw, we know that we're putting them in a variable before we begin doing any modifications. Can we somehow change that? So in order to accomplish these, we have to look at something called pipelines. So pipelines can allow us to break down our report into multiple stages. Each stage can take its output and send it to the input of the next stage. So by doing this, we are now able to scale up individual stages. So we can scale up our process and modification stage while leaving our stage that integrates with the external resource alone. Because that stage is mostly just waiting for asynchronous requests, it's actually not doing much compute. Meanwhile, our process and modify stage is utilizing a lot of compute. This also allowed us to go in and individually make modifications or debug issues on specific stages. So we don't have to look at this one report as a whole, we can now look at specific stages. So pipelines might sound familiar, and that's because the MongoDB aggregation framework uses them. So as we can see here, we have two stages. Our first stage is our match stage, where we're looking for that customer ID and anything that has a start date greater than our start date. And our second stage, we're just projecting the specific name and email. Another example of stages you may have seen or used is on the terminal. So you may have done something like a list and piped it into grep to look for specific files. Or maybe on NodeJS, you've utilized the piping to pipe one stage right into the next. And by doing that, you simply call .pipe. So this is great. We integrate pipes into our application. We have a lot of customers who are happy. They say their reports are coming even faster because we've scaled up the modification stage. However, we've noticed that that customer requesting 1 million users still isn't getting the report. So we're like, what the heck's going on? So we look at our worker and we see something interesting. We see that the RAM increases at a very consistent rate with the size of the number of documents being requested. And it peaks at 1.5 gigabytes and then it crashes because it's exceeded the memory threshold. So short term, we get with SRE and we're like, let's throw money at this problem. Let's give the worker more RAM. And that works until somebody requests more. Or we build a new report that's more complex and it utilizes more memory for even smaller number of records. Okay, so we need to actually solve our real problem is what we figured out. So in order to do that, we identified that we need to start processing records immediately. We need to stop holding on to them in memory in our users variable before we begin operating with them and integrating with that third party. So what we have today is a process that looks a lot like batching. All the records come into memory on our integration, and once we've received all the records, we begin doing the integration mappings. And we then send it down to our process modify stage, which then waits for all the data from the integration stage, begins doing modifications, and when it's done, it sends all the data over the bucket storage. And interestingly, we've noticed that the bucket storage frequently has high latency. So we've seen a lot of times the process and modify stage is actually done modifying data, and it's trying to transmit all that data to the bucket, and it's just taken a long time. But that whole time, all that data is in RAM. And not only is that slow, but it's also costing us money. We're paying for all of this RAM every time that another report's requested. And these aren't complex reports. So the other problem is that it's hard for us to estimate our capacity. So we've gotten reports for what seems like a simple report that ends up building up a ton of RAM usage. Meanwhile, we'll get a request for a very, very complex report that doesn't seem to. And it's because we can't estimate how much data is coming from one stage to the next. It's primarily based on what date range the users requested and how much data is in there, not the complexity of the report itself, not how hard it is to put this data together, but also, we could have at the integration stage larger amounts of data coming from that third party than perhaps another report from even a larger customer. Maybe this customer just has more data with the third party that we're integrating. So we want to be able to build a process that we can properly estimate the capacity that each stage needs, as well as we also want to be able to begin operating on records right away. And to do that, we need to turn to streams. Streams immediately send the record from one stage to the next rather than holding on to it. So by using streams, we can engage all stages of our process, all stages of our pipeline at once. And by doing that, we can begin processing, which is slow compared to the integration immediately. And as soon as the processing's done, we begin that transfer over the slow latency to our bucket storage. So we implement this, and our customers are super happy. People are getting their reports crazy fast, but we still are not getting that one large report. That's interesting. So we thought that streams were the answer. They gave us consistent capacity because we know that the throughput is primarily based on the stage above it. So we thought we were good. Well, interestingly, what's happening here is a thing called back pressure. And here's an example of what back pressure looks like in plumbing. So every time we see any kind of bends, or we see these like welding remains or these reducers, they're all affecting the flow of the water through the pipe. And each one of them is causing pressure, back pressure, on the pipe. So to see an example of this inside our pipeline, we can see here that the process and modify stage, which is the slowest, is having to buffer records. So as new records are coming down our integration stage, they're hitting our process and modify faster than it can do them. So it's buffering up all of these records and it's storing them in RAM, causing really high RAM usage. So now we've identified RAM usage is only high on this specific application, on this stage. It's not high throughout the rest of the pipeline. So first thought is, okay, well, we could put RAM just for this stage, and that would potentially solve our problem if we gave it enough, but it costs us a lot of money. And we've noticed that the issue keeps getting worse. As the larger amount of records that are coming in through the pipeline, the bigger the buffer has to be. And not only does that cause us to have to spend a lot of money on RAM, but it also slows down the worker as the resource utilization gets high. So what we need to do is we need to implement some kind of process that handles the back pressure. So by handling our back pressure, what we do is we make each stage communicate up to the next stage, to the previous stage, that it needs to pause. It needs to stop sending it data. And the previous stage then would be subject to the same issue of buffering. So what it does is it sends up to the stage before it, hey, I need to pause the data. By doing this, we can pause our entire stream, and we can even actually get a benefit of freeing up resources on those other stages. So our integration stage, that application is now no longer processing. It's no longer integrating with data. And whatever node it's running on can utilize its compute and RAM to process some other report that's not currently paused. So we've freed up more resources. We've also slowed down the amount of data coming into our modify, so that way it no longer has to buffer. As soon as it's done, it sends a message that says, hey, resume the stream, and each one of the other stages begins processing and sending data down to it. Another option is we could also split our stream, and we could have multiple process and modify stages that the integration stage transmits to, allowing it to build the report significantly faster, as well as also avoid the issue of high RAM utilization. This significantly simplifies the process of managing our streams. We no longer need to think about peak performance. We don't need to think about what's the maximum capacity can handle. We know that once we've properly implemented back pressure handling, that each part of our stream will not allow it to exceed its buffering limit. So we go back and take a look at our usage now that we've deployed this, and we can see how amazing this is. We've decreased our total RAM usage from over 1.5 gigabytes to not even quite 78 megabytes peak. We also see how much more consistent this is as compared to the other report grew from approximately 60 megabytes all the way up to 1.5 gigabytes. This report's typically within a 4 megabyte range. We are also able to handle very large reports. We no longer have the issue of the application crashing. We can run the report for 10 million users, and while it may be slow, it will always complete. By doing this, we are getting at least a 2 times faster speed just on simple exports, but we can easily be seeing well above a 10 times speed increase when we have a lot of complex data processing, or we have additional stages further down the pipeline that are slow. For example, bucket storage. We may have some kind of storage that's running really slow, but the benefit with our streams is as soon as a record is available, we begin that process of transmitting over that slow. We begin processing our records and immediately transmitting them to the final slow stage. As compared to in batch processing, we wouldn't even begin sending anything over that slow process until everything's done, significantly backing up our pipeline. So let's put it all together. Pipelines help us build maintainable stages for data processing, while streams help us process that data faster, and the back pressure protects our streams from the slowest stage in the pipeline. It also significantly improves our resource utilization. The MongoDB aggregation framework works extremely well with all of this because it's already built on top of pipelines. All right, so I want to show you a quick code sample. And what we have here is we have a stream and a basic report we're going to run. Both of these reports are going to export exactly 100,000 users, and I chose that number because the basic report can complete this without crashing. In both of these examples, all we are going to do is export the data. We're not going to even process it at all. What I want to do is show how significant of gains we can get, even just in exporting data from the database. Both of these are connected to a MongoDB Atlas cluster, and yeah, we're going to give them a shot and see how it goes. So we'll start up both of them, and then I'm going to pull up the performance down here. All right. So as we can see here, very early on, our batch processing here at the bottom is already well above the RAM utilization of the stream. The stream's looking very consistent, just sitting at 75 megabytes. Meanwhile, the batch is just keeps growing every second. And we can also see that the stream is engaging a more consistent CPU amount. It looks like it's averaging anywhere between like 3 to 10%. Meanwhile, the batch sometimes will drop really low, for example, to 4, and now we spike to 14. Later on, we might see spikes as high or above 25%. So the stream not only helps with RAM, but it also helps with our CPU utilization because we are immediately engaging all stages and at a very consistent rate. There are other significant ways we can utilize streams, not just for reporting. We could also, for example, set up a stream that pulls data from MongoDB and pipes it across a socket to a front end, and we could immediately show the user, for example, something like log entries. So we see that we are already about to peak 500 megabytes. I believe that's about the halfway point for the batch processing. I think we're going to get close to a gig. And we've now hit our highest peak on the stream, which was 80 megabytes, but we came right back down into the 70s. So we should be wrapping up our stream pretty soon now. And just to keep in mind, like I said, this is the most simple form. All we have done here is, we've pulled all the users and then we're just writing them to our local file system. So we're not even engaging a slow remote file system where streams would have another massive improvement over batching. So our stream is finished at 110 seconds. And if you just want to take a quick look here at the stream, what we've done is we've set up our CSV stringifier here, and then we've set up our file system, and then we just simply pipe them right together. So our batch is still running, and we're at well over 10 times the max RAM the stream has ever used, and we are still running, and we're starting to see those higher CPU. But it's still that random where, right now we're at 7, we're 3%, but a second ago we were at 40+%. And there we go, we're back up to over 30% CPU utilization. So we should be about to finish up any minute here. We're getting to that 1 gig mark. There we go, we've crossed 1. And it's wrapping up right now. So we peaked at about 1.2 gigs. That last 200 megs looked like it was mostly to do with the CSV stringifying. So that's another interesting thing in the batching. What we have here is we need to pull all these records. And so that consumed a little over a gigabyte just to have all the user records in our local variable. After that, we wanted to stringify all these. So that was comma delimited with headers. And that process alone increased our RAM usage by another 200 megabytes. So as you can see, this is a compounding issue. And then we wrote out the data. As compared to in the stream, since we set up our stringifier and our file and then piped them, every single record came in and went through the stringifier and then was saved to the file right away. So as we see here, the batching process took about 170 seconds. Meanwhile, the stream took 110. And this is the most basic form. We just pulled data from a database and saved it to our local file system. So you should be able to see significantly larger improvements in more complex reports and while working with more outside applications or storage locations. So my name is KazooHR. I hope you enjoyed my talk. I hope you enjoyed the rest of MongoDB Live. I'm super excited that I got to share that with you today. Thank you very much.